We also need to think about some additional practical considerations. For instance, these are the kinds of graphs we use to figure out the class of pump that should be used for a given application. So a pump manufacturer will put out a chart like this, which shows all of the pumps they make and what conditions they're the best for. So you go to the manufacturer and you say, okay, I have a need for 400 gallons per minute and 200 feet of head, and they'll look at this and say, oh, this is in the region for 2AE11. So then you would go to the pump curves for the 2AE11 pumps and figure out the best rotor size, the efficiency, all the other important parameters from the pump curves to make your final design selection. Now, most pumps operate at constant speed. You can see on these graphs we have a 3500 RPM and a 1750 RPM graph. However, there are also variable speed pumps that can change the rotor speed to match the load or the demand for fluid. These allow you to control the flow rate without complex plumbing by controlling the power input to the pump, which allows you to save energy and materials. However, they do require complex, expensive control systems. However, as the cost of electronics is decreasing rapidly, soon these kind of pumps may be very similar in cost to constant speed pumps. We also can look a little bit at the dimensionless analysis for pumps and other kinds of flow machines. So we can introduce some dimensionless coefficients. Phi is our flow coefficient, which scales the flow rate. Psi is the head coefficient, which scales the pump head. And we also have the torque coefficient, tau, although the torque coefficient is basically a combination of the flow coefficient, the head coefficient, and the pump efficiency. And then we also have the power coefficient, which is pi. Now, we can combine the flow and the head coefficients to come up with the specific speed. The specific speed is a measure of the speed at which a pump produces 1 unit of head per 1 unit of flow rate. So high specific speeds are good for axial flow machines, while most centrifugal machines are going to be looking for lower specific speeds. Now, in engineering practice, we also sometimes use dimensional versions of the specific speed, which you can see here. And the reason we use these dimensional versions is because it's easier to make these calculations in the field, where you don't have to do a lot of complex unit conversions. So you can measure these parameters very easily in the field and just multiply them together. They are related by a constant, basically a unit conversion factor, to the actual definition of the specific speed. Now, these dimensionless coefficients form the basis for scaling turbomachinery. But they're mostly useful for incompressible flows, pumps, and certain kinds of liquid-based turbine technologies. Power plants typically use Rankine or Brayton cycles, where the flow can be compressible. So in that case, these dimensionless numbers aren't the best. So we're going to make some additional analysis to look at compressible flow systems. Now, when we have these kinds of systems, we try to minimize the heat transfer, and we're going to neglect all work besides shaft work. And we're going to assume that potential energy is negligible, steady state. And in this case, we can actually find that the shaft work depends on the difference in what we call stagnation enthalpy, where stagnation enthalpy is just the enthalpy plus the kinetic energy. So this is for an ideal compressor turbine. We haven't accounted for efficiency yet. Now, since the density can change, we need to have a little bit of a change in our dimensional analysis. We assume we have a perfect gas. A perfect gas is an ideal gas, which follows the ideal gas law, with constant specific heats. So the specific heat doesn't change. Now, most of the time, when we scale turbo machines, we use full-scale prototypes with the prototypic fluid. So we can eliminate the geometry of the rotor, the diameter, the radius, etc., and some of the fluid properties, like the ideal gas constant or the specific heat ratio, from our scaling analysis. We can also say that the flow in these types of machines is almost always very turbulent, so we can neglect the Reynolds number. And so we end up with a few important dimensionless parameters. However, this is more than we typically want to work with when we're looking at pump curves and graphing performance for turbo machines. So we often convert this to the corrected mass flow and the corrected speed. And we start with the mass flow and we start with the speed, and then we multiply by a dimensionless parameter that's supposed to help us scale those parameters, which usually depends on the temperature and the pressure and the critical pressure and the reference pressure and so on. This allows us to create an operating map for compressible flow turbo machines. It's very similar to a pump curve. We start with this idea of the operating line, which is actually just all of the points of maximum efficiency. So whenever you're operating your compressible flow turbo machine, you want to be operating as close as possible to that operating line. We also have these lines of constant efficiency, lines of constant speed, constant corrected speed. And there's a couple of other areas we want to look at on these compressible flow turbo machines. The first one is choking. Choking is a maximum possible flow rate. Basically what happens is the flow rate gets so fast that the flow reaches Mach 1 at some point inside your turbo machine. That's the maximum flow rate that is allowed in the machine. And so you can't go any faster from that point on, and it basically puts a limit on the flow you can have through your turbo machine. Surge, where you can see the surge line on the graph here, is caused by an adverse pressure gradient on compressor blades. And basically what happens is boundary layer separation and significant vibration. So you can get a lot of loud vibrations that can damage the compressor. So we try to not operate very close to that surge line so we don't have to shut the compressor down for repairs.